Right, then the recording is running and we're looking forward to your lecture about the Monte Carlo event generators.
All right, then I'll just get going. So yeah, thanks. And let's see how this purely virtual CTEC CNET school works out. Usually the school is very active and social, and I kind of hope that through the recitation sessions so we can capture some of that. I'll definitely be around tonight and tomorrow for all kinds of questions that you would have. Right, so let's just dig right in, I think. I think enough people have already connected. Let's get going. So this is going to be a lecture series of 4 lectures. So 4 one-hour-long lectures on Monte Carlo event generators. And I think that's kind of a nice way to start a school, because you might, because I think event generators offer an excellent opportunity to actually learn phenomenology. Not necessarily learn event generators, but actually phenomenology. How do we think about what happens in high energy scattering and in the data taking, say, at the Large Hadron Collider? So the goal of the lectures really is to give sort of give you sort of some basic background on different aspects and algorithms of event generators. And more specialized lectures will take place later in the school. We'd have some about sort of showers. We have some about non-perturbative physics and these kind of things. These general lectures, again, are kind of aimed to be broad, but not too detailed. So really just an overview. Should give you a generic overview and a basic idea of the algorithms that are in place in event generators, such that you can judge, hopefully afterwards, what these event generators can do for you and what they won't be able to do for you. Then in the second part of the lecture, which will happen sort of after sort of a short coffee break, we'll talk about phase space generation and hard scattering, which is kind of at the core of an event generator. Move on in the next lecture, that's going to be tomorrow morning, on towards the Sudakov algorithm, parton showers, and multi-parton interactions. And then finally, tomorrow, around lunchtime, we'll finish off with a bit of patternization. So the process of converting color charged particles to color neutral objects. In general, when there are any questions, there are 2 options. You can either shout them out, or you can write them in the chat. If you write them in the chat, then I might not see them immediately, in particular because I'm in full screen mode. So if anyone is willing to sort of monitor the chat and then screen, if you see a question, then that'd be really helpful for me, and I hope also useful for you. So don't hesitate to ask anything, in particular, given that we're in a very comfy setting. I'm in my home, you're probably at home, have your coffee ready. So we'll just keep that casual. All right, start with the meat of the lecture. To begin with, what really is an observation in particle physics? An observation is something like you measure the average value of an observable by taking sort of a differential cross-section, that is kind of the distribution of particles, integrating that over the momentum quantum numbers of the particles against a test function that is your observable, so the value of the observable at these individual points. So an observable is needs to calculate an observable in quantum field theory, needs 3 ingredients. It needs the differential cross-section, it needs the phase space distribution, and it needs kind of the value of the observable defined at for individual quantum numbers. So what phase space means here is really it's just a sample of all the quantum numbers that you're interested in, say momentum quantum numbers, flavor quantum numbers, possibly if you're interested in something that is unphysical but still useful, color quantum numbers, spin, and so on. So the quantum numbers of the particles in the scattering final state. The differential cross-section is, in this case, basically the transition probability to this particular scattering final state. It's useful for this lecture series to compare this to an expectation value of a particular function in statistics. So in statistics, the expectation value of a function is given by its integral over some random variables that you choose from a population based on a particular probability distribution f. This is very, very similar to what we have in quantum field theory, which shouldn't come as a big surprise because both of them are non-deterministic in their measurement process. So calculating theory predictions in quantum field theory is actually very convenient to do with statistical methods, even statistical mechanics methods. And that's more or less the starting point for what Monte Carlo event generators do for you. So before sort of understanding what is actually in these, hopefully not any more black boxes after this week, is let's think about how we do experiments in particle physics. So in an experiment, we create phase space points on which you calculate our observables in various ways. We can collide two particles and sort of annihilate them, produce a lot of energy, which then distributes itself over a vast variety of fine state particles. So, sort of seen in a slightly different relativistic frame. This is similar to saying, well, we take a particle and we shoot it at a brick, and we see what comes out of the brick at the other end. So that's what is typically called, for example, a fixed target or beam dump experiment. We can also build a huge detector, fill it with water, and just wait until something happens in that detector. For example, if you want to detect neutrino interactions, then a neutrino comes in from the sun somewhere, and we have a big detector, and in the middle of the detector, the neutrino interacts with something and produces an interesting feature. So here, the difference with the two first things is that your interaction actually happens with the detector material, whereas in the first two cases, you have a dedicated beam and a dedicated target. Then finally, there's the other option, which is kind of all the hype these days, that you have a particle, say like a muon, and you just wait for it to decay. And you wait and you wait and you wait until things decay, and you measure the decay products. That is kind of fashionable, or that's interesting right now these days because of the gyromagnetic moment measurement of the muon that was just recently updated and is a bit in tension with our sort of current theory. So interesting. Certainly the first three, so kind of the collision type experiments, the beam dump experiments, and the neutrino type experiments all use event generators in their design and data analysis. So event generators, in this case, are just really statistical tools to create theory predictions. That is slightly different from what you would do on pen when you sort of solve or sort of calculate something on pen and paper, which is in a sense a dedicated calculation. In a dedicated calculation, what you take is you calculate analytic expressions on paper, or very likely also on a computer in order to solve some of the algebra. That is a safe and fast method of doing simple things. Fast in the sense that the expressions that you get in the end are typically very easy to evaluate. Quite tedious in the intermediate steps because you have to do all the analytic or sort of the algebraic manipulations yourself. It's really only viable though for select simple problems, and for that it can be very, very powerful. Monte Carlo event generators, in a sense, take a very different approach. They say we approximate the analytic expressions such that they are amenable to numerical evaluation, and then statistically sample from these expressions on a computer. So we know, sort of in a sense, the population, and we sample from the population of states on a computer. That allows us, if the approximations are easy enough, to use Monte Carlo methods, which I'll describe in a bit, to handle very complex scattering final states and observations that typically you can't just write down on pen and paper. Let's say a 100-dimensional integral, you probably wouldn't want to do on paper. So the analogy between kind of what is a dedicated calculation and what a Monte Carlo calculation is always kind of nice, I think, to think of in terms of what is the resolution that you're sort of interested in. What is the resolution at which you're observing the final state? So in a bit of an analogy, let's look at the coastline of Britain. There, the question is, let's say, for example, how long is the coastline of Britain? Well, the answer is, I don't know. Depends on how close you look. Depends on what your resolution is. So if you're looking only very coarse, then a lot of segments of the coastline of Britain will look rather straight. And you can have a very sophisticated model, very sophisticated analytic model of drawing straight lines, right? So great. If you look a bit finer, well, then you see sort of the, for example, here, the marina in front of Brighton appearing. That is still something that you can probably handle with sort of a bit of modulation on a linear fit. It starts getting complicated, though. It gets even more complicated if you start looking at, say, if you look even in more detail and the quays of the marina appear, or even if the ships within the quay of the marina do appear, or the barnacles on the ships, or the sand on the barnacles. So if you're down to the level of trying to model every grain of sand on the barnacles, on the ship, in the quay, in the marina of Brighton in Britain, then probably you wouldn't want to do that with an analytic tool, but you would want something that roughly describes the average quantity of sand on a barnacle. And Monte Carlo event generators aim to do that by basically being as detailed as possible, as kind of detailed as this kind of grains of sand, but only sort of statistically, in a statistically meaningful sense, meaning that only if you sort of if you average over enough observations will you be able to make sort of concrete predictions. The tool that we use in order to do this are Monte Carlo algorithms. And the reason for that is because they are widely applicable in a large number of cases. For example, in integration, say you want to approximate an integral, a one-dimensional integral of the function f. In statistical mechanics, that is just, well, the average value of f times the integration domain. And the average value you can arrive at by picking a lot of values for f, 100,000, whatever, and dividing by the number of times you've picked or you've evaluated the function. This is the basis of how we work. So if n is large enough, so if the number of samplings of the function that you're interested in is large enough, then you can get a good approximation of this integral. In particular, in this case, the approximation error scales like 1 over the square root of the number of sampling points. And importantly, it scales like this, independent of how many integration dimensions you have. So for one-dimensional integration, you would never do this because you'd have to you have better methods. For two-dimensional integration, you probably also have better methods than Monte Carlo algorithms. But if you look at a 100-dimensional integration, your approximation scales with the number of sampling points rather than the dimension is really a lifesaver. And it's really ideally suited for our types of integrals in quantum field theory. Again, where an observable is, and if you take the differential cross-section and you integrate it against a test function, that is our observable value at a particular phase space point. And you can do that by creating a lot of phase space points, called here phi n, and sort of evaluating their weight, which is the differential cross-section. And then for these two things, so multiply the weight with the value of the observable that you want to measure, and you do that for a large number of points, and eventually you'll get a good enough answer, or sort of statistically meaningful answer for what is the average value of your observable. So what is your measurement? Effectively, Lezouche event files do exactly that. So Lezouche event files take events that kind of like these phi n's, store them in an ASCII in a text format with an event weight. So there are many ways to think about an event, several ways clearly. One of them is really just a collection of numbers, a collection of particle IDs, their so for example colors, how they are related to each other in order to see kind of how they are connected, and therefore their form momenta and maybe masses and so on. This is a way kind of, if you have never used an event generator and you don't really know what an event or what event means, this is a way of thinking about it, a collection of quantum numbers, spin, color, momenta, and so on. Another way of thinking about it is as a linked list of particles that is defined by how the state evolves from a simple interaction to a more complex state that you finally measure in the event generator. And that is the approach that we'll take for the remainder of the lecture, that we kind of look at kind of how is the state of the system, of the scattering system, changing in order to build up this rich event that you see here, for example. Before sort of seeing how this is done, well, the first question that you want to ask is that, well, this looks very complicated. And in particular, if I say 100-dimensional integration all the time, this might not be something that would be immediately easy to solve, even if you have numerical methods. Luckily, the sampling or the event generation of these complicated phase space points and the calculation of the different cross-section is actually, with some hand waving and some theory, factorizable into smaller problems. What you can do is you can ask a machine physicist to provide beam parameters for you, and the parameters of what the objects that you're scattering, or maybe the object that you're sort of dumping into a fixed target, and kind of giving you what is the average center of mass energy, what are the particles that collide, are those particles protons, are those electrons, are those neutrons or pions or whatever. Once this is done, and you know the distribution of initial particles, this part of the event weight factors off. This is something that is kind of something that can be measured, but this will not affect the downstream chain more than by influencing the center of mass energy. The next step is then a Monte Carlo event generator, which takes these beam particles and translates them into scattering final state. That means hadrons, photons, leptons, neutrinos, all of these kind of fun things. Again, once this is done, the generation factorizes, meaning that at this point, the rate of this final state is fixed, and only its distribution over say in momentum or maybe in number of particles, changes slightly by interacting with a detector material. That third step is the detector simulation, which then takes the inputs, hadrons, photons, leptons, and propagates them through the detector, potentially interacting a bit with the material, and so on. Finally, at that state, once this is done, the real part of in a sense, of the simulation is over. In a sense, you have a final state that is as the one measured by a detector. Mostly you can't do anything with that yet because it's very complicated and maybe not directly useful for an easy analysis. So what you do is event reconstruction. You kind of reconstruct analysis objects. You see, okay, these tracks I actually see, these tracks maybe form a jet and so on. And once you form these analysis objects, you can actually analyze. So what typically happens is that A and all the rest is factorized at collider experiments. But it is not factorized, for example, in neutrino experiments, where again the interaction happens directly with the detector material. So all of these three things here, the Monte Carlo event generation, the detector simulation, and the event reconstruction, are kind of smashed together somehow.
Stefan, if I can interrupt you, there's one question in the chat. What are the events, or what events are, if I understand it correctly? You already showed an example of an event. I don't know whether you want to.
Okay. Yeah, let me explain again.
Or maybe Chinmoy, if you want to ask directly, feel free to clarify the question.
Yeah, so maybe I'll quickly go back, and right, if you want to clarify, then just jump right in. So what an event is, again, is I personally, so there are many ways of thinking about it, and whatever works for you is perfectly fine. The way how I think about an event is really a collection of particles, meaning particles given what is their flavor, what is their spin, what are their other quantum numbers like color, and a 4-vector that defines its momentum direction. That is the final state of the scattering. So in a sense, let's say you take an example, you scatter 2 protons. Those 2 protons might annihilate and produce an electron-positron pair. And that electron-positron pair might be accompanied by a lot of photons. So what the event would be is an electron, a list of, or kind of, let's say, 2 or 3 particles. The first one being the electron and its form momentum, the second one being the positron and its form momentum, the third one being the photon and its form momentum, and so on and so on. And that event would then later on, if this is only sort of if all of the momenta are very high energy, these momenta might split up further in order to distribute energy over a larger set of final states. That would also then be kind of a second step in the generation and maybe in the interpretation of what is this event. So this is kind of what I mean by the second thing. So indeed, if you look into this big, beautiful mess that is a Large Hadron Collider event, you'll see what happens is there is, at the very hard process here, red hard process, a Z boson created that decays into an electron-positron pair. And then the initial state of these things actually starts radiating gluons, which further radiate gluons and so on, and then later on get bound into colorless final states. Again, several ways of thinking about an event. For me, the most concrete one is just a list of 4 vectors and particle IDs. Does that clarify it a bit? If I don't hear anything, I'll just go on.
There was no further question in the chat. Oh, yes, it is clarified, is the answer in the chat.
Okay, cool.
Thanks, Stefan.
Cool. Also, thanks for the question, because that allowed me to take a sip of coffee.
May I ask an additional question?
All right. So.
Hang on. Simone, you are very faint. Simone is trying to ask a question, but you're very faint. I think Stefan didn't hear you.
I may try to speak.
It is indeed very faint. I can't catch it.
I can write.
Could you try to repeat again? I just sort of upped my volume.
Wait.
I think it's probably okay if you really speak up, then it's probably just.
The question is that there exists a standard format to store these events in the MC community.
Ah, right. Yeah. That there are several, indeed. And it depends on kind of what interpretation of the event you have or kind of what is the most interesting feature to you in these events, which format you will actually use. And for example, these formats, this format here. This is actually sort of a codified format called a Lasuche event, which typically is used for transporting a relatively simple hard scattering, so the hardest, highest energy scattering type of event between different generators. There are other formats that look more like this linked list here. For example, the HEP-MC format, which is typically the output of a general purpose Monte Carlo event generator, say like Perwick, Pythia, and so on. And then there are other formats to handle the output of the detector simulation and so on. But there are definitely standard formats. And the reason for that is, of course, that if we don't have standard formats, then each analysis would have to be specific to a particular generator or simulation tool chain. And that would, of course, be very horrible, because then you couldn't sort of combine things in order to make the best out of the different types of calculations. Which maybe brings me to my next slide, which is that indeed the Monte Carlo event generators landscape is very rich. So it does make sense to have sort of standard interfaces between generators, or sort of between generators and analysis tools, for example, in order to make the best out of this very rich landscape. So in neutrino physics, there are tons of generators, in cosmic rays as well. What I'll mostly focus on in this lecture is the view from LHC physics. Why do I do that? I think this is a relatively good proxy of how you should think of how you should think about event generation, and then the additional sort of complications in neutrino physics, like cosmic rays or heavy ions. You can maybe see how you could build those around an LHC physics generator. So I've every now and then in the slides you will see kind of this small kind of comment that there is an exercise. And one thing that you could, what I was thinking is, one thing that you could do is during your gather town sessions in the evenings, you could chat about these comments. I don't expect anyone to solve these exercises, but just to get together and see if this was an interesting question to you and how you would solve it together with your friends. So one thing that I would highly recommend you to do is to try to pick a generator out of this list that you don't know, that is in a field that you don't know nothing about, and just Google it and share your findings with your friends later tonight. Okay, right. After this assignment, let's actually look at how high energy collision general purpose Monte Carlo event generators, well, that's a mouthful, to do their type of simulation. How do we think these different types of phenomena that we see in the detector come together? The first thing we think happens when we collide particles is that a high energy scattering, breaks the beams apart. But if there's no high energy scattering, then it's very difficult probably to detect the final outcome. And it's maybe also not a particularly interesting outcome, depending on, of course, the person that you ask. So a high energy scattering breaks the beams apart. For example, in this case, creating a gluon and two quarks. Let's say, for example, these beams are protons or neutrons and so on, hadrons, let's say. Once the beams are broken apart, you've now created a couple high energy particles. These high energy particles will initiate a cascade of radiation in the vacuum. Why? Well, you can think of this in a sense similar to electrodynamics. An accelerated charge radiates. So that will happen both in any type of electromagnetism-like theory, for example, also in quantum chromodynamics or in the weak force. Every basically particle physics theory if they're bosons, they will be radiated in a cascade in the vacuum. So this has nothing to do with transition radiation in a material, but it's rather transition radiation in the vacuum itself. However, at the same time that you have a hard scattering that breaks the beams apart, once you have a hard scattering that breaks the beam apart, it's very, very likely that secondary scatterings occur at almost at the same time. Basically, now you've taken a snapshot, you've taken two beams, you collided them. In colliding them, you took basically a snapshot of the wave function of these beams, and there was a large excitation in that wave function that produced this high energy breakup. If there's a large excitation, there might be long tails in the wave function that still can lead to secondary interactions. That is what's called multiple interactions in LHC speak. Again, these produce accelerated particles, so they would radiate further and initiate some kind of radiation shower. At some point, though, and kind of you already see that in my slides, a phase transition occurs where the average energy per particle is small enough that the coupling of a QCD, the strong force, becomes non-perturbative. So it becomes the meaning, kind of in a sense, you could think of the individual particles itself lose their meaning, and rather the potentials that are formed by the particles, or the force fields that are formed by the particles, make more sense. In a sense, think of it as at very high energy, you have very few, you have a couple of excitations on your on a lake, a couple of waves on the lake that are the gluons. But at some point, these, if you have a lot of waves, these will form coherent new structures. Let's say, for example, solitons and so on, that act as the new degrees of freedom. So what will happen at some point is, when the average energy is small, is confining potentials form, and these confining potentials lead to the nucleation of excited and unstable hadrons. So hadrons are kind of the colorless objects that QCD tries to describe. These excitations, or unstable hadrons, will then have to decay further into stable states. These stable states, again, might then undergo some type of radiation, for example, from radiating additional photons, if they are still high energy enough. And eventually, outside of the eventually, once this all of this decays and radiation is terminated, the event generation itself is terminated, and you move on to the interactions with the detector, and from that, the event reconstruction and the construction of analysis objects and the analysis of an event. For example, this event might have led to the production of 3 jets of collimate of particles, one here, and maybe one here, that could be used for analysis. For example, to check, did this event contain this particular gluon here, or was that indeed was this not a gluon but a colorless object like a photon? Questions so far on this this breakup of event generation?
Just in that minute, there is a question in the chat. Can you please explain what multi-parton interactions are?
Ah, very good, very good. I'd love to. So the multi-parton interactions are kind of these pink thingies here. So the way how we think about this is, well, there are 2 ways of thinking about, maybe 2 ways of approaching the question. One of them is to say multi-parton interactions are a phenomenon that is necessary in order to explain observed data. Meaning there is tons of evidence that the structures that we see in data are not only, we can't only explain by having a single hard scattering that distributes its energy over over particles by a radiation cascade. That's one way of thinking about it. It's kind of, this is the heuristic way. We need something, we need more than one interaction in order to describe data. The kind of more, maybe more theory way of thinking about it is that if you have two composite objects that collide, and that there is no real reason why you'd expect these composite objects to only interact in a single point. They might interact in more than one point. And that is maybe a kind of more sort of theory-based philosophy of what multi-parton interactions are. There are just several interactions. There's not only a single interaction and a secondary, but also a tertiary, a quaternary, and so on. So there are at the LHC, for example, there are even up to 30 interactions occurring between the protons that collide. And the maybe more quantum mechanical way of thinking about this is, well, you have two protons that collide, given that they are sort of at very high momentum. They are very Lorentz contracted, so basically at some point they overlap like pancakes. And in one point of the pancake, you have some raisins hitting each other. Once that happens, it's very likely that this sort of shock of that the wave functions interact with each other, this type of measurement will induce another type of measurement or another type of interaction between the constituents of these composite objects. Did that help a bit?
Maybe there were two follow-up questions kind of related to what you just said, and which fits with the LHC picture you were just giving, maybe to distinguish between multi-parton interactions and pile-up, whether that's the same or whether this is different, whether this is different partons or pile-up interactions.
Good. Very good. So maybe I'd be a bit heretic and say for now that multi-parton interactions are like the pile-up of a single proton-proton interaction. So multi-parton interactions are kind of multiple partons within two fixed protons interact with each other. Well, pile-up is multiple constituents of the beam of kind of a bunch of particles that you collide interact with each other. Why is this a bit heretical? The reason is that pile-up typically is uncorrelated, meaning that if you have two bunches of particles crossing each other, the probability of having a, say, third interaction between protons at the LHC doesn't depend on the probability of having a second interaction or the first interaction. Whereas if you look at multi-parton interactions, the probability of having a secondary interaction between partons does depend quite a bit on the probability of having a first interaction, simply by saying, by the reasoning that if you have a very hard interaction, have a first interaction that is at very high energy, you have a very large disturbance of your wave function of this system. So it's very likely that something other than just the single interaction happens, simply because you have a large disturbance in your wave function. But a very good question. So it's a very similar phenomenon. One of them, pile-up, is more or less uncorrelated, whereas multi-parton interactions are correlated. Pile-up is between the constituents of a bunch, and multi-parton interactions between the constituents of the protons or the hadrons that you collide itself.
And there is actually one more question in the chat about distinctions of underlying or of multiple parton reactions. Namely, I've heard the term rescattering in the past. Is this just another name for MPI?
Very good. It's a component of that. So there are several. So think about it. There are several aspects of what type of interactions can occur, indeed, and one of them that could occur. That's when we think. One of them is that kind of you have a scattering of 2 particles going into, say, 2, 3 particles, followed by a secondary scattering of 2 particles going into 3, 4 particles. But you can also have a scattering of 2 going to 2 particles, followed by a scattering of 2 particles whose final state then gets absorbed by the first scattering. That would be something that is called parton rescattering, and is indeed a part of what you could think of as different phenomena that contribute to these secondary interactions. This particular case is something that has been looked at before and was found to be, it was inconclusive if it had played a big role in the modeling of LHC results. Another aspect of rescattering, which has nothing really to do with the secondary interactions, but rather to how do the stable states at the very end of the event generation interact with each other, is hadronic rescattering. So if there are tons of hadrons here flying around, it can very well happen that they interact before they ever hit the detector material. For example, right, there's a nice little hadron here that points almost towards this. So if this here is fast enough and this here is slow enough, they might hit each other and scatter and interact with each other. That's hadronic rescattering. And that is typically something that is very important if your hadron density is very high, because then this becomes more and more likely. But it's not something that is related to multi-parton interactions per se. Let me see, how am I doing with time? No, not too bad. All right. Go ahead, Frank.
Can I just test exactly? I wanted to test whether you can see if someone raises their hand. So I would encourage everyone, if you have a question, because it's much better if you ask it directly to Stefan rather than I just trying to translate what your question is to Stefan. So if you want, you can use the raise hand feature in the Zoom button reactions. There's a raise hand tool. So then Stefan sees that someone wants to ask a question and can stop and let you ask the question. So that might make it easier for you rather than typing in the text.
Yeah, very good. All right,
okay.
So 2 participants. I don't know your names, unfortunately. So participant 1, please speak up.
Jay, you're raising your hand. I think I was the other one, so you should go ahead.
Okay, hi, thanks. Can you hear me?
I can hear you, yeah, go ahead.
Okay, so I was about to ask, so you mentioned how the earlier how the perturbative processes can be modeled using Monte Carlo. So does the same apply to this non-perturbative hadronization and other things, or?
We'll go into that in detail later, but basically the idea is the same. Indeed, you will use Monte Carlo methods as much as possible in order to take the quantum numbers that you have and distribute them over sort of a larger set of quantum numbers. And for example, let's quickly go back. What do I mean by that? Right here, you started out, for example, with this perturbative kind of very high energy scattering, and that initiated a radiation cascade. So the way how I picture that in a kind of trying to solve an integral type of mindset is that this will distribute these original momenta, these momentum quantum numbers, over sort of more particles, like all of these blue guys here, and do that by Monte Carlo method. The same thing, kind of the same philosophy will hold in this case, where you have now sort of you've taken kind of your initial kind of partonic or sort of high energy scattering seeds, you convert them into these potentials. These potentials, again, are just, in a sense, collections of particles that you know would produce new states coherently. This is maybe how best to think of a potential. So it's a collection of particles, maybe sort of a couple of gluons, a couple of quarks, and kind of a force field that you think binds them together, that would then sort of produce a new type of object with certain quantum numbers that then gets again sort of split into smaller objects with and the quantum numbers of the large object distributed among the smaller objects that would be hadrons in this case. And indeed, so the idea of event generation is that in each of these steps, you have kind of a subset of the particles that you would have in the final, or a subset of the states that you would have in the final result. And each of these subsets is generated through Monte Carlo methods, through sampling. And so we'll go through how exactly these samplings work and kind of what are the algorithms in just a bit.
Okay, thanks.
Cool. Okay, so let's do that then. So from the technical point of view, or this kind of chain of phenomena, kind of this that we can separate the bits and pieces of producing the final state, kind of looks like you have a probability distribution of producing from the beam a certain final state. This probability distribution, in the sense of statistical mechanics, factorizes into small bits. So, for example, the probability of picking sort of the particles that two particles that will collide out of the beams, maybe more if you do think about multi-parton interactions. This typically is something that depends on very few quantum numbers, and hence on very few random variables or integration dimensions, maybe 2, 3, whatever. Probably most likely only 2, namely maybe 2 and let's say 4. So the momentum distribution of these particles within the beam, and by beam I now actually mean kind of the proton or the hadron that collides, not the bunch. And so the momentum distribution of those, and maybe their identity, meaning their flavor quantum numbers, for example. So this is how only adds a couple of few additional degrees of freedom to integrate over. Then these particles collide and produce few partons. And by partons now I mean quarks, gluons, maybe photons, leptons. I'm very loose with the term partons here. Again, this, since it only would produce few and high energy partons, this will have an integration dimension that is maybe sort of, it needs maybe tens of integration variables. Maybe let's say if you produce 3 outgoing particles, you'll need you need 3n minus 4, meaning 8 integration dimensions. So that's not so bad. Probably not something you'd want to do on on a sheet of paper, but still quite doable with not so complicated numerical methods. Then these few partons initiate these radiation cascades and produce many partons. This is where the number of dimensions really starts to proliferate, and you go into the hundreds of dimensions. These many partons then collate to hadrons, maybe unstable or excited hadrons. Again, there you have quite a jump in dimensionality, that you're maybe up to thousands of integration dimensions. And these hadrons then decay into stable particles. These decay chains can be very, very long, meaning that really in this last step, the number of integration dimensions explodes, so that you might be in the tens of thousands or even hundreds of thousands of integration dimensions, depending on how long these decay chains are and how high a scattering energy you initially had. So traditionally, only Monte Carlo methods would actually be viable to solve the problem of distributing phase space points according to this type of factorized probability density. So we really need to learn about these numerical methods in order to make any sense of what an event generator actually does. I should note, though, that for very special cases, deep neural nets actually have a potential of simulating some special cases here, given that they have tons and millions of parameters that you could tune in order to actually produce produce from the beam a final state without all these intermediate steps. But no one has done that so far, so we'll see what happens in the next couple of years. So some basic overview that I want to give you now is about numerical techniques, so that we get a feeling about how we tackle this large dimensional integration. So we'll look at how to pick samples from a probability distribution, as goes by the name of inversion sampling, or how to pick samples from probability distribution that we have trouble integrating, so they have trouble doing analytics with, going by the name of rejection sampling or hit or miss sampling. And we'll actually continue to learn some more tricks, some more of these numerical methods in the next lectures. All right, how am I with time? Yeah, I think that's okay.
Yeah, there's about 10 minutes in the first slot left.
That's okay. And I can even enjoy my cold coffee. So first thing, imagine you have a state of particles. Say it's a radioactive isotope that maybe will decay and can decay in several ways. How do you pick one of these decays to happen? Let's say you have 3 decay channels, channel 1, channel 2, and channel 3. And you know the probability of channel 1 to occur, channel 2 to occur, and channel 3 to occur. The way how you pick which channel occurs, such that if you pick often enough, on average, your result is correct, is that you draw a random number between 0 and 1, and you pick channel 1 if that random number times the sum of the probabilities of all the channels is larger than the probability of picking, or the probability of channel 1. You pick channel 2 if through a random number times the total sum of probabilities is between the probability of channel 1 and the probability of channel 2, and so on. And you repeat this as often as you like. Simple enough, right? Makes intuitive sense that if you now sort of have picked 1,000 times, then you probably have only kind of this much events in the first channel, or this much of decays in the first channel. You have many more decays in the second channel, and you have very few decays in the third channel, simply because the chance of hitting this interval here is smaller than the chance of hitting, say, the second or the first interval. But you might ask yourself, well, if I know these decay channels, I know their probability, why should I go through the hassle of actually doing this? Why should I go through the hassle of sampling from these probabilities? And the answer is that once you've done that, and you've done that often enough, the rate, each of these decays that you produce comes with the same weight. The rate of the channel is instead given by its population in the sample. So you maybe have, let's say, 3 instances of a decay here, 5 instances here, and 2 here. The rate is given by the population, no longer by the probability or the weight or event weight, if you want. Every event indeed has an identical weight, which is the sum of all the probabilities. It might just happen that, it will happen that you get more events, you have a larger population of decays of the second type in the sample than you have of decays of the first or the third type. So this is statistically quite nice, or sort of for analysis quite nice, because you will not, your analysis will not. Oh, so when you create an analysis, you will not occur large fluctuations in what is the weight of an event. Kind of large. You will not. You'll not find very large fluctuations in the double value that you would have to add to a histogram, which is good, because then you know that at some point you can stop and say, okay, I agree, I probably have found all the things I need. I can stop my sort of generation of these decays after 100,000 events or so. This is called the discrete transformation methods. And typically an event generator is used to pick, for example, between different scattering processes, or indeed decay channels of unstable hadrons, or potentially for unweighting, meaning if you have generated a lot of phase space points, meaning events, with the differential cross-section as their event weight, then these differential cross-sections can be very different depending on what is the event, what is the phase space point. But with this method, you can basically say, okay, now I have generated 1,000,000 events. Give me 1,000 events that for which the population of the sample determines what the rates of the channels are, rather than the event weight itself. That's called unweighting, and would typically happen. Would typically try to produce unweighted event generators as much as we can, so that you don't have to worry about large fluctuations of numbers that you have to fill into your histograms. The same algorithm also applies when you want to pick a continuous index. So note, right, in this case, we picked an index. We picked index 1, 2, or 3, depending on a random number. We can also apply the same algorithm when picking a continuous index y, which translates to picking a random variable according to a distribution. For example, picking a phase space point according to a distribution. In this case, the cumulative distribution, so this C of y, or what kind of the C that determines which channel we picked before, will now be the integral of our probability distribution, like this. For simplicity, assuming now that the probability distribution is actually normalized to 1. Again, now if I can say I want to pick a specific index y, then these discrete integrals that we had previously start shrinking and shrinking and shrinking, such that in the end, picking y is using a random variable to pick y is identical to setting the cumulative function distribution to the random variable. So C of y will be r, which then gives us a way to extract what is the index by inverting the primitive function, this cumulative function, on the random variable r. This is called inversion sampling, because we take the cumulative function and we construct an inverse function in order to extract our index y. So in this way, we have distributed indices y, or sort of phase space points y, if you'd like, according to the probability distribution that we've started out from. In exactly the same way as for this discrete transformation method, that we have sort of transformed the probability distribution into a decays given a certain probability distribution into a sample with certain populations of decay channels, Now we've transformed the probability distribution into a sample of y given by and kind of different y values depending on the population, or the population of different y values given their likelihood according to the probability distribution. So that's called that's called inversion sampling, and is used again quite heavily in event generators. However, very often we're actually not that lucky. So this is a purely sort of analytical method, if you want. However, we're often not lucky enough that the invertible primitive function, so C, the inverse of C, the cumulative function, exists, or exists in a definite solution. There can be multiple solutions, and we wouldn't know which to pick from. So very often we actually need a more flexible algorithm in order to distribute indices according to a particular distribution. And so here's again a small exercise. Given these formulae, try to generate random variables x larger than 0 according to an exponential decay distribution. So we can circumvent the issue of not knowing the inverse of our integral of the probability distribution by something called rejection sampling, or hit or miss. So the basic idea is you use a simple distribution from which you draw values of x, and then you adjust the rate of these x values in the sample once you have created the value. So you for example, produce 5,000 x values, and then adjust the rate of these of the x values that you produce in order to recover the rate as would have been given by a more complicated function. A simple example of that is to calculate pi from random sampling. So with that, you can take random variables that you sort of distribute according to a uniform distribution between 0 and r, and you only accept the pair of random variables if the sum of their squares is smaller than r squared, which is the definition of what is within a circle. And then the accepted pairs will be the number of accepted pairs that you will get will be proportional to pi over 4. So from this way of sampling and accepting, you can calculate pi over 4, so a more complicated, an integral of a more complicated function, right, which is certainly more complicated, and it's not only single valued, by adjusting the rate of the pairs that you store. As a final thing for this lecture, typically this is still not enough. Typically, a uniform sampling, so sampling something just like this uniformly in a particular interval, is very bad efficiency-wise. So typically we need something that is more advanced in order to sample from the distributions that we're really interested in. Let's say, for example, you have a distribution f of x that rises quite rapidly. Look at this is kind of my way of writing a log scale. This rises quite rapidly as x becomes smaller. So if you sort of pick x flat, with a uniform distribution between, say, between 0 and whatever 1,000, then what will happen is that you will reject very few proposals if the x happens to be picked here, and a lot of proposals down when you accept here. So you generate a lot of proposals out here for large values of x, but you would also throw away a lot of proposals. So this is a very bad use of your resources. So a more clever way of doing rejection sampling is to combine it with inversion sampling. So the idea being that inversion sampling allows you to sample from a simple distribution, So maybe if you take the simple distribution and then you again weight it down, so you sort of decide on how large a population do I actually want only after the fact that I've created X, say my phase space point. Then you can look at much more complicated functions. So you assume a simple distribution, g of x. Again, x could be a phase space point or so. And you assume that this is larger everywhere where you want to sample x than the interesting, more complex distribution f of x. And so you write f of x as g of x times the ratio of f of x over g of x. This ratio will be smaller than 1. So if it's smaller than 1, and it's actually between 0 and 1, then you know, then you have a good idea of how to sort of get rid of the additional things that you oversample. So you use inversion sampling to draw x from the function g. Then you use another random variable r, and you reject the variable x that you've drawn if f of x divided by g of x is smaller than r. So meaning that, and if, for example, if g of x is very, very close to f of x, then this ratio here would be very, very close to 1. You'd very likely throw a random number that is not extremely close to 1, right? It's uniformly distributed between 0 and 1. So in this case, if g of x is very close to f of x, you would accept the point. If g of x is very far away from f of x, you would again reject it. So for example, you're looking at kind of a simple function, let's say g of x being a logarithm and f of x being this complicated function here. There are some cases, say out here, where you would draw from g of x and very likely actually keep this variable and store it somewhere. However, there are cases where g of x might be a pretty bad overestimate for f of x, and then you would throw in this region, you'd throw away a bit more phase space points. Once you've done that, once you've used these kind of 3 steps, or this assumption and these 2 steps, now x is distributed according to your more complicated function, f of x. And this really is excessively used in Monte Carlo event generators. It's almost the core of what we would call a Monte Carlo event generator. So just as a comparison, if you now look at how much gain do you get from the variance, how much gain do you get, how kind of, in a sense, how much do you have to throw away in order to get a good sample, then for uniform sampling, this is really bad. It depends on 1 over square root of n, like the Monte Carlo method that we saw before, but also in regions of large variance, so something where you kind of very, very much, say your integrand f of x is steeply falling, the sampling gets worse. For importance sampling, so this kind of combination of reduction and inversion sampling, your variance will depend on how good is your overestimate, your approximate t of x, approximating f of x. If this is very good, your variance can be very, very small, meaning that the calculation is going to be very efficient because you'll throw away very few points only. All right, so third exercise. Generate random variables between 0 and 1 minus epsilon, where epsilon is a small parameter, with distribution 1 plus z squared over 1 minus z. And hint being, use a simpler denominator for to get g of z and apply this algorithm. This is a typical problem in Monte Carlo event generators, because this is actually how you would, for example, generate gluon emission or photon emission in the radiation cascade. Okay, so this brings me to, with quite a bit of overhead, I'm sorry, I didn't realize that, to the end of lecture 1. And
yes, Yeah, thank you very much, Stefan. And I didn't want to interrupt you because it was almost finishing up. But I think we're running a few minutes later than planned. So let's also restart maybe 5 minutes later, and let's meet again at 35 past.
Okay.
And then we can also, if there are questions, we can also take questions probably at the start of the next section.
Exactly. So if people have questions and want to type them in the chat, then I'll definitely look at them now.
Cool. Thanks a lot. I stop the recording now and restart it when we reconvene.